I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics,
medicine,
nature,
or
space, time,
the brain,
life,
the universe.
This week, we are rounding off our month of extreme shows. We've been extremely cold, extremely deep, extremely fast, and extremely curious. Now it's time for some extremely high science.
Plus, sniffing out methane on Mars, and scientists have been making sweet music with proteins. But why? I'm Adam Murphy.
I'm Katie Haylor, and this is The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
Now, you've probably heard of a remote-controlled car. But what about a remote-controlled stem cell? A team at the University of Birmingham have just launched a project to use magnetic nanoparticles that can be glued onto receptors on the surface of cells and used to control where those cells go in the body and what they do.
Alicia El-Haj, who is leading the initiative, presented the work at a conference in Cambridge this week. By using a magnetic field, the magnetised cells can be guided to where they're needed and the magnetic field pulsed to make the cells transform into new cell types or secrete growth and repair factors. Chris found out more.
So I'm interested in cell therapies, how we use cells to treat patients and cure disease. And the problem we have is how to control cells. How do we actually make cells do what we want when we put them in the body? So my technology is a platform technology where we control cells.
Remote-controlled cells?
Yes, that's right, because the whole aim is to be able to control them from outside of the body.
I was joking when I said that. Is that what you can really do? Actually dictate where cells go and what they do when they get there?
Yes, so what we use is the principles of magnetics. We use magnetic fields to actually move cells around the body. We tag the cells with magnetic nanoparticles, which are very, very small, and then we can actually visualize them as well using MRI technology.
Tell me about these nanoparticles then. How do you get them to stick only onto the cells you want to control, and what are they made of?
So we attach the cells outside of the body and we attach them to specific receptors that are located on those cell types. And they're made of iron oxide. And actually we naturally have iron oxides in our body. So it's something that the body doesn't reject.
Essentially then, I would have some cells taken out of me, or they might even come to someone else then, and you add this collection of nanoparticles to the cells in a dish, and what they glue on in the right place on those cells.
So we can use peptides, small molecules that we can attach onto the surface of the particle, and that binds to the receptor on the membrane of the cell. And what's nice is the principles are based on mechanics. So receptors in our body are actually mechanically activatable, which I don't think people know as much about. And so we can actually move the particle and it operates the mechanical switch on the receptor, leading to a downstream response.
Once the cell's been decorated with the nanoparticles, how do you get them back in the body then? Do you inject them?
Yes, so what it aligns itself with is an injectable cell therapy. We inject into an organ such as the knee for cartilage repair or into sites of bone damage for osteoporosis, and we can actually localize it in an injectable format.
And how do you then dictate to the cells, I want you to go to here, but not to here?
So we can use magnetic fields to target those cells to specific regions of the body. That's the principle. The particles get attracted to the magnetic fields and get localized to the sites we want them to.
Do they essentially drag the cell there then?
Yes, basically.
And if you make those magnetic fields wobble, does that mean you can make the cells wobble? And that could in turn activate those switches?
Yes, that's the idea. We change the magnetic gradient. Then the particle moves in the gradient, and it can be very small movements. And it sets up forces on the receptors in the order of 6 to 8 piconewtons. And those forces are enough to activate and open the cell's receptors.
How big's a piconewton? Because I'm aware that 1 newton is if I lift up an apple, that's 1 newton, isn't it? Roughly speaking, it's 100 grams. So how big's a piconewton then?
Small.
Yeah, so you're getting out of jail free with that. But okay, so we have these cells. They've got these particles on the surface. You can vibrate them with these magnetic fields. As a result, you're throwing these switches backwards and forwards. How do those switches, though, change what the cell does?
So the particles attach to the receptor, and when they move, they activate the receptor and you get a downstream signal. And that signal can be a variety of different signals. But what that does is lead into effectively a gene activation, and then you have an expression of different proteins. So what we want to do is actually control cell type. If you think about it, you have cartilage, bone, different cell types in your body. And what we can do is take these stem cells that could be anything, and by changing the receptor activation, we can then turn them into bone, we can turn them into cartilage, we can turn them into different types of tissues. So you can imagine we can inject in the cells, we can then remotely change the way the cells behave and then form tissues in the body. That's the ultimate aim.
And there's not a chance that the nanoparticles could fall off the stem cell, fall onto a heart cell, and I accidentally turn my heart into a lump of bone and it doesn't pump so well.
No, actually, eventually the particles are internalized in the cell, and what we've studied is that it changes the way the particles are, so they no longer are able to bind to other cell types.
And so there's no danger that a person who's going on their flight and goes through the metal detector or whatever at the airport is going to accidentally activate all their stem cells downstream of this, and they arrive at their destination, they don't look like their passport photo anymore.
People always ask me that question, am I going to attach to the fridge magnet? I think the point is that we have quite a lot of iron in our body anyway, and actually the amount of iron we're putting in is nowhere near the level of what you'd eat in a steak. And the other side to it, I think, is basically that anything will be cleared from the body originally, so you won't be permanently magnetized.
And I can't push these cells into an abnormal route of development. They're not going to become cancerous through being stimulated in this way, for example.
Yeah, and that's things we have to be really careful for. We have to actually check that isn't the case. So far in our hands, we have not seen any evidence of that happening.
And is this far off? Because it sounds a little bit space age.
It does, but actually we've just been received a significant amount of funding, so we're going to be developing this over the next 5 years, and we would like to think we can reach patients in a 5-year window.
It's extraordinary how fast this field is moving. Alicia El-Haj there talking to Chris at the Health Horizons Future Healthcare Forum in Cambridge.
From space-age technology now to space itself, and the quest to look for life on our nearest planetary neighbour, Mars. This goal got a boost this week. NASA's Curiosity rover, which has been trundling around on Mars since it landed 6 years ago to study the surface for the chemical fingerprints of life, suddenly detected a powerful whiff of the gas methane while it was sampling the Martian air. Methane matters because it might be a hallmark of microbial life, both past and present, but it can also be the product of other natural chemical processes. Katie spoke to David Rothery, who's a planetary geoscientist with the Open University, where he's been keenly following this story.
Curiosity inhales some of the Mars atmosphere into a chamber, and it bounces a laser beam to and fro across that chamber and looks at the specific absorptions of specific wavelengths of light and relates those to the concentration of gases. It's called a tunable laser spectrometer because it can change the wavelength of light they're using to tune it to exactly what the particular molecule they're looking for should be doing.
Okay, so this laser beam gives you an output related to how much gas you've got.
Exactly. It's been well calibrated on the Earth, and they've got some onboard calibration as well. So the measurements it's making are pretty robust. I've spoken to team members. They're not doubting the numbers they're getting.
What are those numbers? How much methane was in this spike?
The recent spike got up to 21 parts per billion. That's not a lot of methane at all, but it's a lot higher than the normal background. Normally, we've been seeing methane, with the Curiosity rover at least, less than 1 part per billion.
When exactly was this seen, and how long did it stick around for?
What excited people was when a plume was seen in the middle of June, but it disappeared very, very rapidly. It was gone by the 22nd, 23rd of June. And that's very crucial information. If it disappears so quickly, it's telling you it wasn't a large volume of methane. You're not sniffing the edge of a really extensive plume. You're in the middle of a small plume, which can very quickly be blown away or be diluted by the local atmosphere. This methane must have been released very, very recently for it to be detectable. It could have been trapped underground for millions of years before escaping. Ultraviolet light acting on carbon delivered by meteorites or micrometeorites can give you methane. Reactions between warm water and rock below ground can give you methane that can leak out. So methane can be produced by a variety of processes, or it could be being generated today by methane producing microbes, which would really like to be the case because we'd love to find some life on Mars.
What are scientists doing to better understand these outbursts? Are there any seasonal patterns emerging, or is there anything that can be inferred?
There's a seasonal pattern to the methane at the Curiosity site. I mean, Curiosity is moving around, but not very far on the grand scale of things. Methane rises and falls at the 1 part per billion level with the seasons. Now, Curiosity's seen, I think, 3 different spikes now, with the latest one 21 parts per billion. And methane's also detected from spacecraft orbiting Mars. The most sophisticated spacecraft now is the Trace Gas Orbiter with an instrument called NOMAD on board. And I understand that is looking very hard to see if it can find this plume that was seen on the surface. The trouble is, from orbit, you're well equipped to see large plumes. A tiny plume covering a few square kilometres that was rapidly diluted by the wind, you won't see from orbit. But they're looking, and that will help them pin down the nature of the plume.
As a planetary geosciences expert, what do you make of this? Should we be excited?
I'm interested because it's the biggest plume we've seen at the surface, so we need to build up a database of how quickly they appear, how quickly they can disappear, and that will help us track down how locally the methane is sourced. I think it's going to turn out to be very locally to where the rover is. I think these are just small bursts of methane. We need something on the surface that can do an isotopic study of the methane, because living processes will concentrate certain isotopes of carbon and hydrogen over other isotopes, and that won't be the case for abiotically produced methane. So we need to fingerprint the methane, which we've yet to do with instruments we don't yet have on Mars, and then we can really tell, is it life doing this or is it something just chemical?
David Rothery there from the Open University, and he was speaking to Katie about reports this week of a methane peak on Mars.
Staying with the space theme, time now to debunk a myth conception. And this week, Matthew Hall has been investigating the controversial claim that space travellers experience zero gravity.
3, 2, 1, 0.
Space. It hosts countless environments that are detrimental to our health, but ironically is home to one of the most sought-after astronomical phenomenon to experience: zero gravity. Space is a mere 100 kilometers away from us at all times, yet only those trained as sufficiently as astronauts have the privilege to feel weightlessness in space. If you are willing to pay a considerable amount of money, there is the option to experience simulated weightlessness using an airplane traveling in parabolic flights. The dips in the trajectory of the plane have been designed to recreate zero gravity. But this isn't real zero gravity, right? Buying tickets for these parabolic flights would be like buying grandma's cookies in a store. They'll get the job done, but they are not the authentic, gooey, mouth-watering cookies from grandma. Well, that's where the misconception lies. The idea of zero gravity, or no gravity at all, doesn't exist. Let's look at the International Space Station. Contrary to popular belief, the weightlessness of the astronauts in the ISS is not due to reduced gravitational forces. The pull from gravity at their height is actually almost the same as here on the ground. The truth is, they are actually falling. Every single second the ISS is in orbit, the football field-sized hunk of metal is actually in freefall, and so are the astronauts inside. And yes, I referred to an American football field. The fact that these astronauts have not plummeted to their doom is thanks to the speed at which the ISS orbits the Earth, a casual 7.5 kilometers per second. The station moves so fast that the Earth's surface curves away from their freefall path. Essentially, the ISS is a large projectile that keeps missing its target. To help better visualize the effect, imagine a cannon on top of a really tall mountain that has an unobscured view in front of it. You want to make the cannonball go as far as possible into the clear space ahead of you, but you can only fire horizontally. How do you do it? By increasing the speed at which the cannonball is launched, it can then cover more horizontal distance before gravity pulls it to the ground. Now imagine your cannon has limitless power, and you keep adding more energy to increase the speed of the cannonball. Eventually, the ball will reach a speed great enough to circle around the Earth and land behind you. Add more and more speed, and the ball will keep circling and never touch the ground, despite the fact that it is falling. That is essentially what an orbit is, an object in a seemingly endless freefall. One other key concept to debunking zero gravity is that gravity is literally everywhere. Look at the moon, for example. Earth's gravity is what keeps it in orbit around us. The ISS is between the moon and Earth, which means that the station still experiences the force of gravity from Earth. Say you require a rocket and blast off away from Earth's gravity. The sun has a gravitational pull that extends a couple of light years in all directions. Let's boost up the power of that rocket and say we make it out of the sun's gravitational field. Even still, there is gravity from the Milky Way galaxy keeping you and billions of other stars in orbit. Let's get even more ambitious and say we leave the Milky Way's ring of gravitational influence. At that point, there are so many billions of other galaxies floating in the universe that you will have entered their ring of influence. No matter how far you could theoretically go, gravity will always be there lurking in the background, making the idea of zero gravity impossible. So go ahead and buy those plane tickets, because that weightlessness is exactly the same as seen in space. It won't be an endless free fall like the ISS, but it is an out-of-this-world experience nonetheless.
Thank you to Matthew Hall for burying that myth for us under the influence of gravity, of course. Meanwhile, if there's some suspicious-sounding science you've come across, you can drop us a line to chris@thenakedscientist.com and we will take a look.
Coming up, in space, no one can hear you scream, right? We'll be finding out. Literally. Stay tuned.
But first, this week, scientists announced that they can map out the structures of important proteins, things like the hormone insulin or even spider silk, using music. This gives them a new dimension for studying how proteins work and how we can use biotechnology to tweak proteins to do other important jobs, as Ankita Anirban explains.
We think of eggs as providing us with a good source of protein. But in fact, proteins are everywhere. They're the basic building blocks of all living things. They're found in plants, animals, and even food. Jelly is, in fact, an edible protein. Proteins come in many shapes and sizes. They can be ordered structures, like a corkscrew, or more randomly shaped, like noodles cooking in water. And for larger objects, they can literally look like brick and mortar structures. Now Marcus Buehler and his team at MIT have found a way to translate these protein structures into music. But first, I asked him, what is a protein actually made of?
Proteins are made from building blocks called amino acids. There are 20 unique amino acids. You can imagine them being like bead on a string. Each bead that you add to the string is one of those 20 amino acids. And which amino acid is actually added onto the string is defined by the DNA that is the blueprint for how this particular protein is made.
But what does this have to do with music?
So the way we understand how these amino acids actually sound like, and if we do a very careful analysis, we found that these molecules aren't static. They continuously vibrate. These vibrations can be calculated based on quantum mechanics. And what we found is that each molecule has a unique frequency spectrum. And once we make that audible, each molecule has a very particular way it sounds like.
So that's apparently how a lysozyme molecule sounds. That's a protein which you find in egg whites. So what's actually the point in doing this?
By listening to the proteins, we can begin to link the structure of proteins, how they fold, what kind of function they have, with how they sound. And we can begin to edit the protein and actually change the sound and maybe design new proteins or understand how mutations in proteins affect their functionality. And many diseases originate through mutations of proteins. And in the audible space, we can listen to different proteins, a healthy protein, the disease protein, and we can begin to understand what are the changes that actually cause this breakdown of functionality and maybe cause disease.
Sounds like there may be very useful applications that come from this work.
Proteins are everywhere in nature, and a lot of times they actually act as materials. And these give us an opportunity to create materials that are not only made from renewable resources, but they also are resilient. They usually have very strong mechanical properties, and they can degrade automatically. With this new approach of being able to understand at a very different level how we can design proteins, we might be able to create new materials that have more sustainable properties, even better functionalities that are sustainable, resilient, and can be recycled in a very simple way.
Given that there are 20 different amino acids, and we can arrange them in any way, surely there are millions of possibilities for new kinds of proteins. How do we know which are actually useful?
We not only have translated these proteins into sound, but we've also used artificial intelligence to help us understand the language that nature speaks. We train the neural network, we then let the neural network create new sounds, and we translate the new sounds back into the protein sequences, and then we try to make these proteins and try to understand what they actually do and how they function. And possibly, hopefully, finding proteins that actually perform even better than the natural proteins that nature has created.
That was Marcus Buehler. And the paper setting out that work is in the journal ACS Nano. If you want to have a play around with these tones, the research group have released an app called, appropriately enough, Amino Acid Synthesizer, and you can get it from Google Play.
Speaking of food, a new ultra-cheap food sensor can instantly tell whether your chicken thighs are still good to eat. It's called the paper-based electrical gas sensor, and it might just save supermarkets wasting some of the millions of tons of food they throw away every year. Plus, it can even connect directly to a smartphone. Firat Gouder from Imperial College London is the device's inventor, and he told Phil Sansom how he came up with the idea.
Paper carries a substantial amount of water that would allow us to do, wet chemistry without ever adding a single drop of water to paper. So you need essentially liquids to do chemistry oftentimes. And this liquid is absorbed from the moisture in the air. It turns out that the environmental gases can actually interact with this layer of water that's absorbed in paper. And by measuring just the electrical properties of this layer of water, we can determine if a certain gas is in the environment.
How does the gas affect the electrical properties?
For example, if there is ammonia gas in the environment, it can actually come and then dissolve in this layer of water into ions. With increased concentration of ions, there is also an increase in conductivity of this layer of water. So by just measuring the ionic conductivity, we can essentially measure the concentration of, let's say in this case, ammonia.
Oh, so like if you measure how well the piece of paper conducts electricity, that goes up if there's ammonia in the air.
Precisely, yes. The sensor itself is most sensitive to water-soluble gases, and ammonia is a highly water-soluble gas, so it's really, really sensitive to ammonia. But it is also sensitive to other water-soluble gases, such as trimethylamine and even carbon dioxide.
And it's basically just paper, right? So that's why it's dead cheap?
They cost about 2 cents. And through high-volume manufacturing, we estimate that probably we can decrease the price about 1,000 times.
What are you going to do with it?
So we have a very inexpensive sensor that performs really well. So it was just, to me, that obvious that this would be a really useful technology in, sensing spoilage and freshness of meat products. Because meat is protein-rich, when the proteins decompose, they release a lot of ammonia and trimethylamine and so on, nitrogenous compounds.
So are you anticipating that you can use this as a sensor inside the packaging of meat to tell whether it's actually gone off or not?
Yeah, precisely. So I started talking to various managers at grocery stores just to see, what they think about this. Because clearly the literature says that, the food waste is a big problem. Well, first of all, this was a really difficult thing to do because it turns out that most grocery stores were not really interested in, sharing their stats with an outsider. They don't want to tell people how much food they throw away. So I had to actually, build personal relationships with some of these managers to, I guess, gain their trust. One of the things that I noticed is that the meat products, which are considered to be high value, they already contain various electronic components that are embedded inside the packaging itself. And the most known example to this is actually near-field communication tags, such as the ones that are used in Oyster cards and so on. And this allows retailers to really monitor their inventory. And because our sensor is electrical, it turns out that we can integrate our electrical sensors onto these disposable near-field communication tags that are already in place with meat packaging. By making components or making, smart tags that would allow them to also monitor the freshness of foods, they think that they would be able to save a lot more money and throw away a lot less food.
That was Frat Guder with sensors made from just paper. He published an article about the invention in the journal ACS Sensors. And if you'd like to find out more about any of the news items discussed this week, all the transcripts and papers can be found on our website, nakedscientists.com.
Now, if we open up the mailbox this week, we had an amazing email from an extremely long-time listener. Mark Evans from Hillsboro, Oregon, has been listening to us since summer 2000. Mark says, when I heard the date for your team's experiment involving a high-altitude balloon, which, if you've been listening to The Naked Scientists, you'll know what we're talking about, and we'll come to it in a bit, I was reminded of the children's book by David Weisner, June 29th, 1999. Is your launch date a coincidence, Mark says, or is someone on the team also a fan of the book? To my shame, I haven't heard of this book. Adam, have you?
If it's someone on the team, it isn't me. I'm just astounded by the coincidence.
Thank you so much, Mark, though, for your loyal listening, and we really hope you're continuing to enjoy the show.
For more from The Naked Scientists, head to our website, thenakedscientists.com. You can follow us on social media, we're at Naked Scientists, and why not leave us a review wherever you get your podcasts.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions. Now, we've been talking extremes over the past few weeks, and this week is our final extreme show, Extremely High. Take a listen to this.
That's perfect! That's perfect. That's the right amount of ascending rate that we want.
More on that later.
But first, many of the world's population are lowlanders. But what happens to our lowlander bodies at high altitude? And how could understanding the science involved actually help us to treat critically ill patients in hospital? Well, Cambridge University physiologist Andrew Murray works on exactly this. Andrew, what are you holding?
Well, Katie, I've brought along a collection of Tibetan prayer flags. Blue representing the sky, white representing air, red representing fire, green is water, and yellow is the earth. You find them all over Nepal. I mean, that's why I brought them along. It reminds me of many fun times and exciting times we've had doing science in Nepal, all the way from Kathmandu, right up to the high passes of the Himalayas, and even flying on the summit of Everest.
So before we hear about your adventures, what happens to the human body as you ascend?
Well, there's a real distinct time-dependent response as we go to the mountains. When you land, when you step off an airplane at about 2,000 metres, your body instantly responds. You start breathing harder to try and bring more oxygen in. That's the challenge, of course. Your heart starts beating faster to deliver more blood around, therefore oxygen around the body to the tissues, such as the muscles that need it. And then given enough time, you might see more changes. So after a couple of weeks, your body would be making more red blood cells to carry more oxygen.
Your work involves having healthy people trek up Everest, and then you do science with them. So, first of all, what is it like?
Takes your breath away, quite literally. It's the views are absolutely stunning, the scenery, the wildlife. But more and more, you notice yourself getting breathless, not being able to push yourself to quite the same extent as you do at sea level. I mean, around 2,000 metres, which is the altitude where the airport is in the Everest region, if you fly in there, you do feel it pretty instantly.
Wow, so you haven't even started climbing and you're out of breath?
Yes, absolutely. And then there's steps, a nice steep flight of steps just coming away from the airport to really let you know that you're in the mountains.
Once you're actually up there, what science are you doing?
So what we've done in the past is set up labs at lots of different altitudes, and they'll trek on a regimented ascent, so nobody is going any faster than anybody else. And then we'll do things like put them on exercise bikes. We'll measure how much oxygen they are using, and from that we can calculate their efficiency. And of course, we wouldn't be medical scientists if we weren't poking and prodding them with needles and taking blood, lots of samples to study back in our lab. We had a first big expedition in 2007 where we took over 200 lowlanders trekking to base camp. You see some people who do really rather well, who acclimatise and can function very well at altitude, and others who do rather less well. And we're trying to understand why that is. And with large numbers, we were hoping we could get a handle on the genetics that might underlie that.
What are the general applications of doing this kind of research on healthy people at high altitude?
That's always been the goal of our group, is to understand then why it is that some people do well with less oxygen at altitude and some do less well? And is it the same factors at play that determine whether a patient in the intensive care unit who's struggling with a lack of oxygen, whether they will pull through and survive or whether they will succumb to their illness? The story about altitude acclimatization when we first started doing this was largely, okay, it's all about trying to get more oxygen through the system to the tissues to fuel the metabolism. So it's all about the heart rate and the breathing rate and the red blood cells. And actually what we found is certainly not the full story. It's much more about how your tissues use the oxygen when it gets there. It's how your metabolism is finely tuned to deal with low levels of oxygen. We find that the same thing may very well be useful to a patient. I mean, if they are in hospital and their heart is not working properly, they've got low levels of oxygen in their blood, that oxygen getting to the tissues, it makes a lot of sense that tissue would use the oxygen more efficiently. So what we're looking at in some of these critically ill patients is how their tissues are changing the metabolism to deal with low levels of oxygen.
So what have you learned then so far, paralleling these two situations?
Yeah, so looking at the patients, I've been working with colleagues from Extreme Everest who are based at the Royal Free Hospital in London, and we actually see many of the same patterns of change both at altitude and in the clinic. So the muscle starts to decrease its capacity to use fat as a fuel. We think of fat as being an unhealthy thing. Actually, it's the most important fuel in the body. We store most of our fuel as fat. So you've got to have a good reason to shut down your ability to use fat. And the problem with fat is that it's quite oxygen hungry. To get energy in the form of ATP out of our fat, it requires quite a lot of oxygen to do that. So we've seen evidence in both settings that the tissues are switching away from fat towards more oxygen-efficient fuels, perhaps glucose, for instance.
Is it incredibly far-fetched to say you could maybe capture a mechanism or something and distill it into a drug that you then give to people who are critically ill? What are you hoping to achieve?
Well, that would be the ideal outcome, of course, is that you could help a patient who perhaps wasn't dealing with the low levels of oxygen to fine-tune their metabolism to deal with that. But interestingly, I think this work has already made a big impact in the clinic in that previously the obvious response to dealing with a patient with low oxygen was to ventilate them, to give them pure oxygen to breathe, to try to bring those oxygen levels back up. And interestingly, the recent research has shown that that isn't helpful. In fact, it may even be harming the patients. The oxygen in high concentrations is actually toxic to the body. So instead, we're going for a bit of a middle ground. And the clinicians I work with talk about something called permissive hypoxemia. Hypoxemia is low levels of oxygen in the blood. So we're allowing the patients, in other words, we're allowing them to deal with this low level of oxygen, to adjust to it. Maybe they're shutting down their body's oxygen requirements. And there's probably a Goldilocks zone, a sweet spot at which they want to be. We're not going to take all the oxygen away, but finding out what the right amount is probably the most obvious and easy application.
Now, you've actually ditched your snow boots for a lab coat. What are you working on now?
Really, in the last few weeks, we started a study looking at high-altitude placentas. So these are placentas from women living in either Colorado or in the Andes. So we're looking in La Paz in Bolivia. And collaborators have been collecting these placentas. They've been preserving them, freezing them, and then flying them over to our lab in Cambridge, where we've been looking at the metabolism of the placenta, and particularly the mitochondria, these molecular powerhouses, and how they are using the oxygen to make cellular energy to support the growth of the developing fetus. As pregnancies take place at higher and higher altitudes, the birth weight of the baby tends to fall. So on average, for every 1,000 meters you ascend, baby's birth weight is about 100 grams lighter. Now, this isn't quite true for some high-altitude natives. So if you look at the women in Tibet and Nepal, or you look at the women in the Andes who are giving birth, their babies are still lighter, but only by about 80 grams. So they're relatively protected against the low levels of oxygen, crucially. But why that is, we don't really know, and there's a number of possible explanations. It could be to do with the blood supply. It could make it easier for the oxygen to get across the placenta to the fetus. It could be metabolism. They could be using the oxygen more efficiently. Or it could be things like antioxidant molecules that protect them against the free radicals, these reactive oxygen species that could be damaging in high quantities and which are produced in low oxygen.
So is there anything then that can be applied to people who are having a troublesome pregnancy?
Well, that's the ultimate application, is if we can understand why it is that these women can give birth to relatively healthy babies, even at high altitudes, we can apply some of these findings to troublesome pregnancies back here at sea level, where conditions like preeclampsia or intrauterine growth restriction might also alter oxygen supply to the fetus.
So we're going to have to invite you back to find out what's going on.
Yeah, hopefully we'll have answers in a few months' time.
Andrew Murray from Cambridge University, thank you very much.
Now, it's not just humans who have adapted to the high life. If you think climbing in the Himalayas is a challenge, you've got to be impressed by this.
Perhaps most famously in 1953, when Everest was climbed for the first time, a member of that expedition actually said that he'd seen geese flying at the height of Everest.
That's zoologist Charles Bishop from Bangor University, and the geese he's talking about are bar-headed geese. Katie spoke to Charles to find out how on earth these geese survive and thrive on these extremely high migrations. About a decade ago, he and colleagues went to the Mongolian breeding grounds of these hardy birds in order to better understand how they're capable of making these journeys.
Well, we're very lucky that ducks and geese go through what's called a post-breeding molt, which means that they drop all their flight feathers for a couple of weeks while they're raising their youngsters. So we can use canoes to corral them into nets and catch them in reasonable numbers.
I'm actually quite scared of geese. How easy is it to put a tag on a goose that probably doesn't want to be tagged?
Actually, bar-headed geese, not only do they look wonderful, kind of white and grey birds with the two black bars across their cheeks that makes them famous and a yellow bill, they actually have a very docile nature. So we had some tags that gave us global position. We could track them every hour or so. And over the journeys they were taking, the migration could last over 100 hours of actual flying in total over many weeks. We were also interested in how tough are these journeys, and in order to understand the kind of physiology and the mechanics of the flight itself, we had accelerometers that gave us wing beat frequency. It doesn't change a lot in a goose, but when it does change, it indicates a big change in power output. So small changes in wing beat frequency would tell us that the birds were having to work much harder. And we could also estimate how deeply they flapped. So they would also increase wing beat frequency at the same time they would actually flap in a deeper, what we call an increase in the amplitude of the wing, so in creating much higher forces. But this is hard work, of course. And then the heart rate we can use also as a proxy for energy consumption or oxygen consumption. We'd actually flown some geese in a wind tunnel many years prior to this, which was very fortunate, where we'd correlated oxygen consumption against heart rate.
Crucially, you had to get your tags back again. So did that involve just going back to the same breeding site and getting back in your kayak?
Yes, so unfortunately we couldn't download the tags, so we did have to recapture birds in order to obtain the tags. In fact, the GPS ones were satellite-based, but in order to get the accelerometers and the heart rate, we did have to recapture the same birds. So, of course, we lost a lot of tags because we didn't always see our birds, or we couldn't always capture our birds.
Take us through your findings then. What did you learn?
We found the birds were very, very sensible. So they only seemed to fly as high as they needed to. And we called it the roller coaster strategy because they would effectively follow the underlying terrain. So when there was a high ridge and a barrier, they were capable of going over it. But we only recorded a maximum height of 7,300 meters directly with GPS. And they wouldn't stay high at those altitudes, not more than multiples of minutes. And then they would descend again as the terrain changed. This meant that they actually stayed as low as they could most of the time, within a few hundred meters.
Why wouldn't you just do your ascending and then just stay as high as you need to and fly over the mountains that way? Why adopt this roller coaster strategy? What's the advantage?
We concluded from this that the costs of staying high were sufficiently difficult. So the heart rates we were getting, and a goose's maximum heart rate's around about 500 beats per minute at sea level. At altitude, we're not too sure, but we did record heart rates over 400 beats a minute and at maximum 460, but only very rarely. And at altitude, that might be just very, very hard. The air's getting thinner as they go high, oxygen's hard to obtain, and the forces they need are getting harder to generate. So thrust takes you forward, keeps you moving, gives you flight speed, and then of course lift keeps you in the air and supports your weight. So they were going down whenever they could to be in denser air where oxygen was more available and generating the forces was easier. With humans, of course, we have to go to the mountains weeks beforehand before attempting something as high as Everest. Colleagues of mine have put bar-headed geese at rest into an atmosphere of only 5% oxygen. The equivalent of being at the top of Everest is about 7% oxygen. Sea level's 21% oxygen. And they were okay, which no human could do. Also tended to fly at night, not in the day. We weren't expecting that with the geese, in that we kind of thought that they might use winds that might assist them. So if they could get a tailwind, you'd be covering the ground much quicker. Cuts the cost of the total journey.
Why would it be beneficial for the geese to fly in darkness? I would have thought it's just more difficult to see where you're going.
Possibly you can avoid predation by flying at night. Another possibility is that it's much colder, of course, and it could drop 20, 30 degrees C. The effect of that would be to increase air density. So it would be effectively like flying maybe 500, 800 meters lower. So by flying at night when the air is cooler, air is dense. So again, generating forces is easier. Oxygen availability also increases.
So how are birds able to cope with getting the oxygen into their bodies, which seems to be more difficult the higher up you go? How do they compare to humans?
Birds seem to be better adapted to high altitude. The lung systems and the ability to circulate oxygen through the body, it does appear to be innately superior. Their lung systems are fundamentally very different in design. They actually have what we call unidirectional flow, so it passes through the lungs from one side to the other. It doesn't expand and contract like a human lung, but it does have associated air sacs that permeate throughout the body of the bird, and they expand and contract. And they act like bellows. So when the bird breathes in, it fills up some air sacs. Then when it breathes out, those air sacs empty and actually pass the air through the lungs tissue, and you get gas exchange, oxygen uptake, CO2 output. Then when you think they're breathing in again, they're actually pushing that air out to the forward air sacs, and then finally it all goes out on the second out breath. Probably makes bird lungs more efficient, perhaps at altitude in particular. The surface area for that gas exchange is probably twice as great as most mammals.
And bar-headed geese have fine-tuned these processes even further, even having larger wings than other geese to allow them to reach these incredible heights. That was Charles Bishop from Bangor University. Coming up, we've launched Your Screams 120,000 feet up in the air. But how did the team get on? And did the kit survive the trip? We'll be finding out.
In order to listen to my voice through your radio, smartphone, smart TV, or even Katie here in the studio with me amidst these computers, you're using electricity. And with a growing global population, increasing power consumption, and an urgent need to reduce fossil fuel usage, where will we get sustainable energy sources from in quantities that meet our needs?
One option is nuclear. We already have nuclear fission plants here in the UK and around the world, but fusion, the other side of the nuclear coin, isn't yet a feasible way to power your telly or the kettle to make your morning cuppa. So how sustainable is nuclear fusion as a source of electricity? Where will we get it, and how does it work? Physicist Nick Walkden is a fusion expert from the UK Atomic Energy Authority based at the Culham Centre for Fusion Energy in Oxfordshire. Nick, first of all, how does nuclear fusion actually work?
Fission and fusion are two sides of the same coin. In fission, we're taking very big elements and we're splitting them apart. And it turns out that when they get split apart, they weigh a little bit less than when they're together. And that difference in their weight turns into energy, so we can extract energy from them. In fusion, we're doing the exact opposite. So we're taking two very light elements and we're pushing them very, very close to one another. When they pretty much touch each other, they cling together and they form a new element. And it turns out that when they cling together, they're a little bit lighter than when they're separate. And we can extract that change in weight as well as energy. But to get fusion to work, we have to get these things very close to one another. And they really do not want to be close to each other. So we have to get them to very, very high temperatures so that they're whizzing around, colliding with one another. And that's what we're trying to do in our lab down in Culham.
How safe is fusion compared to fission?
It's inherently safe. So in fission, you get fission to work basically by taking a lot of fuel and putting it next to each other. And the fuel produces neutrons. Neutrons create more fission. That fission creates more neutrons. And you have the chance of having these meltdown effects. We don't have that in fusion. We have to supply the thing with heat for it to work. And we only have a limited amount of fuel. So we put a certain amount of fuel into the machine. If all of that fuel fuses, then we have no more fuel to create any more fusion. And it doesn't matter how hot the thing is, it's not going to create any more fusion. So we have to continuously refuel the machine. There's a study that was done by the ITER organization about this, and they found that a fusion power plant would have an effective radiation outside it that was 1,000 times less than the ambient radiation that you'd see. And if the worst possible containment breach of a fusion power plant actually happened, and someone happened to be standing exactly at the location of that containment breach, they'd receive a radioactive dose about the same as eating a few bananas a day for a year or living in Cornwall for a year. So it's an inherently safe fueling option.
So the tricky bit is keeping it going as opposed to it running away from you.
Exactly. Fusion's kind of funny because we can do the two ends of the thing. So we can get things to fuse and we can extract energy from it, but keeping that process going is extremely tricky. And that's really been the challenge over the many years that people like myself have been working on this.
And how do we make it do this consistently?
So we puff a load of gas into the chamber of one of our devices. Once we start pumping heat into it, we develop this thing called a plasma, which is a soup of electrons and ions whizzing around the place. And we use very, very, very high magnetic fields to keep everything in place. We heat this thing up, we continue fueling, and eventually we get to the kind of fusion relevant temperatures and these things start to collide. And once they start to collide, we start to get fusion going. So we can keep it going as long as we can fuel the machine.
What kind of temperatures are we talking?
Sort of 100 million degrees Kelvin. We're talking 10 times hotter than the sun. When JET is running, one of our machines, it's the hottest place in the solar system.
Wow. Now, how sustainable are the ingredients needed for fusion, and what are those ingredients?
So the ingredients that we use, or we will be using in the reactors of the future, are deuterium and tritium. They're both like hydrogen, but we've added extra neutrons. So in deuterium, we add one extra neutron. And you can find deuterium in seawater. Something like 1 in every 6,000 atoms of hydrogen in seawater is actually deuterium. Tritium is not natural. It doesn't come through natural processes on Earth. But it turns out we can get tritium from lithium just by bombarding lithium with neutrons. If you take all of the lithium in a laptop battery, for example, and a bath full of seawater, you've got enough potential fuel there to power your home for about 20 years.
That'll do me, one bath. When this comes around, will people actually be able to afford it?
Current projections are that when fusion becomes a reality, it should be about as affordable as nuclear fission is now. But of course, this is an emerging technology, so we're still a couple of decades away from seeing fusion electricity on the grid, and there's decades of innovation still in line to start bringing that cost down. And once we build the first fusion reactor, the 10th becomes a lot cheaper, and the 100th certainly becomes a lot cheaper than that.
The big question, of course, is how green will this be? We don't want another kind of fossil fuel type energy coming around.
Absolutely, and this is really, really one of the big gains from nuclear fusion. So the fuel sources themselves, or the reaction itself, has no carbon in it. So the product we get back out the end is helium. Helium is currently actually quite scarce around the globe, so this is probably a good thing. The only carbon we'll spend in nuclear fusion is building the machine itself.
What kind of timescale are we looking at before we have fusion-powered televisions in our house?
So there's this old anecdote that fusion is 20 years away, and it's been 20 years away for 50 years. It's nice to be able to say, actually, fusion genuinely is around 20 to 30 years away. There's this machine being built in the south of France called ITER at the moment. And when ITER comes online and starts running, it will be the proof of principle. And once we've proven the principle and we've proven that fusion can produce electricity, then we can start building reactors and start seeing it really impact our day-to-day lives.
Nick Walkden, thank you very much, and hopefully it won't be that long before my nuclear fusion-powered cup of tea.
Well, we've been talking about this for a few weeks now, and it finally happened. On the 29th of June, we launched our balloon into space. They say that in space, no one can hear you scream, but we wanted to actually test that for ourselves. So after months of collaboration with engineers from Brunel University, we attached a loudspeaker and a microphone to a helium balloon and sent it up to 120,000 feet. Phil Sansom recorded Chris explaining the story.
Well, the idea of this is to send a balloon to the edge of space. And the reason for doing that is that we want to test the theory that in space no one can hear you scream. The rig has been built by Dave Ansell.
So there's a square-based pyramid made out of dowling, held together with cable ties. From this is suspended on springs a loudspeaker at the square end, and a little bit further down a little tiny microphone in a lump of brass to try and give it a bit more mass.
So they are hanging in space but supported by the springs and the elastics. They're not connected to each other, and they can see each other, but there's no way for the vibrations to travel out of one and into the other. The rig's been built by Dave Ansell, and the software has been written by Omar Gad.
The biggest challenge for me was getting the device small enough and getting a power source that can power all of this.
This thing has got to get to 120,000 feet. It would easily go over the top of Mount Everest. So we need to make sure that whatever we do, we can cope with low pressure and low temperature. We bought a cheap speaker off the internet, and then we went and bought a microphone that cost about £8. And pretty quickly realised that an £8 microphone was not going to cut it because it was rubbish. So we went and bought an £80 microphone, and that was much better.
And so I recorded myself screaming. That was recorded with the mic, and now we're going to play what the mic recorded.
So it's playing the audio of the screams, and it's also recording the audio, and we're also recording other things like temperature, pressure. There is also a satellite transponder on it, because we need to track this thing, and we need to know where it's going, because we've got to go and retrieve it, and we have no way of controlling where it comes down apart from watching the weather and following it.
That noise is coming from the receiver, and the receiver is receiving data from the transmitter. So that noise is actually, ones and zeros being sent across the air. And then on here, you'll actually start to see, okay, here, look, it says temperature. It'll then give you the temperature, altitude, latitude, and longitude.
The weather for this is critical. When something's going on a 4-hour flight, all the time it's up in the air, it's subject to wind. But it's pretty windy up there regardless. So it's definitely going to travel across the country. So we may have to do a bit of driving to catch up with this thing. If the wind suddenly changes direction and turns west, then the whole lot's going to go in the ocean and we're going to lose everything. I'm dead excited about this. I don't think anyone's done it quite the way we're trying to do this before. So this is quite cool because it's a first. Do you know, it's been really good fun. Right, well, it's Saturday the 29th of June. Just got in the car. We have to go to the West Country to launch the balloon because the prevailing wind direction is towards the east. So this balloon should come down somewhere over Birmingham-ish. I'm optimistic, buoyant.
Hello. Good to meet you.
Yes, so now we finally arrived. We're here in this field. We've got a very large cylinder of helium, which is what we're going to put into the balloon.
2, 1, go! I'm Dr. Konstantinos Banitsas for Brunel University. This is a project that has 1,000 things that can go wrong, and only in one scenario you can actually retrieve it. Everything has to work right.
We've got the device we've built, which is in a big polystyrene box, which the balloon is going to carry up to 120,000 feet.
We're going to have 2 mobile phones in there and a GoPro to actually take video, so we're going to put those in last. You have to be absolutely sure that everything is secure because we can't tell how crazy the weather might get up there.
Stop.
Yeah, we're ready. We're ready to launch now.
Okay, 10, 9, 8, 7, 5, 8. Oh. Yes! Yes! That's perfect!
1,047 meters after probably, 5 minutes? I'm now going to run the prediction, now that we've launched it, to see exactly where it's going to end up. Okay, so it's going to land in a place called New Cross, near Wolverhampton. One team should now get going, and we will probably clear up and chase after it.
Okay.
Well, I'm Tim Pilgrim at Brunel University, and I'm the press officer that originally helped Omar get in contact with Chris to set up this whole thing. So we've now reached the outskirts of Birmingham, and we've just received some exciting news that the balloon has started to come back down again. So we've obviously reached peak. Fingers crossed we should be at the landing site before the balloon gets there. Oh, it's already landed?
It's in a field right next to a river.
Oh, fantastic.
You guys are probably going to be the first ones there.
Cheers.
Bye.
Well, that's exciting. So where is it?
We found it exactly where we were supposed to find it. And this is the best case scenario. It just lands in the field somewhere, no danger at all, and it's here.
Here it is, the payload, in the middle of a field. We actually lost telemetry. Had it not been for the Find My Phone app, this is how we actually found the device.
Well, we did it. We have succeeded. We actually got our device up to the edge of space and we got it back again and we've got all the data. What did we find? Well, if we look at two screams, here's the first one. This one was recorded at the ground. Children, come and clean your room! And you compare that with this, which was recorded at 33 kilometres up, just before the balloon popped, where the pressure is 10 millibar, so only about 1/100th of the pressure at the Earth's surface. You can hear that the two are dramatically different. The second, where the air is very thin, is really quiet. So, the logical conclusion is, were we to have carried on going up even further, the air would have continued to get even thinner. We would eventually have reached a point where there would be so few air molecules bashing into the microphone, it would barely move and you wouldn't be able to hear it. Case closed. But we have made a special page on our website with all of the raw data and the recordings, as well as other measurements we made, and you can go and take a look at that. Interestingly, we've got the profile of the carbon dioxide levels as we go up, and we think, on our graph, you can see the effects of the M4 motorway and the city of Bristol just upwind of where we were taking off. If you want to go and have a look at it, it's nakedscientist.com/balloon.
Wow, I can't believe they actually found it again. That's pretty amazing.
Yeah, I'm astounded it landed where they thought it was going to land and didn't end up in the sea or someone's garden with a dog. They got real lucky. It's great.
And of course, an amazing amount of prep went into it before the launch. Thank you to everyone involved in that project. And if you want to see the images and the video the team recorded from the balloon and listen to the sounds from space, we've set up a special webpage at nakedscientist.com/balloon. So do go and check it out.
Now, to finish this week, Heather Jameson has been looking at the highest sounds and the highest hearing on record.
The highest note ever sung by a female is often attributed to Mariah Carey's song Emotions, in which she hits a G7. That's a G note in the 7th octave. But the record for the highest note hit by a male trumps that by nearly a full octave. In December 2017, Wang Xiaoling reached an E8. That's higher than most pianos go up to, but whether the sounds could actually be described as singing is another matter. This pales in comparison to the highest notes in the animal kingdom, though. That record is claimed by the clear-winged woolly bat, which can reach a maximum frequency of 250 kilohertz. That's almost 50 times the human record. And where Mariah Carey is famous for having an impressively large vocal range, the bats can sweep through a frequency range of up to 170 kilohertz, which is over 50 times Mariah's range. These bats also share the record of world's fastest chatterers with many other bat species. They emit repeated calls at a rate of up to 1 every 5 milliseconds. That's 12,000 every minute. But the bats aren't just gossiping. They're searching for food using sound. They listen carefully to the echoes to work out how far away an object is, what direction it is in, and how big it is. Why does such a high pitch help with this? Well, the clear-winged woolly bats live in tropical forests, so they need to track bugs and other prey in the dense undergrowth. The high frequencies make the bat's sonar beam very focused and short-range. Scientists believe this may help the bats scan the foliage bit by bit and to concentrate on a small spot where prey is, while suppressing distracting background echoes from the vegetation. The bats' calls are way above the hearing range of humans, but moths have evolved to be able to hear the calls of bats in order to avoid being lunch. The two have been locked in an arms race throughout the ages. As evolution in bats raises the pitches of their call higher to avoid being overheard, evolution in moths pushes the upper limit of their hearing range up to match. But one species of moth, the greater wax moth, has seemingly outrun the competition by a wide margin. Scientists were perplexed to discover that this moth could hear sounds up to 300 kilohertz. That's higher than any animal is known to make, bat or otherwise. Scientists don't know why the moth would have evolved to detect such high frequencies. And the mystery is driving them batty.
Thank you, Heather. And if you've got a chemistry conundrum, physics thought, or biological brain buster you would like us to get to grips with in our usual question of the week slot, you can send it in to chris@thenakedscientists.com.
And that's it for this week. Thanks very much to Andrew Murray, Charles Bishop, Nick Walkden, and everyone who took part in the balloon experiment. That sadly brings us to the end of our Extremes shows. But next week, we're taking a closer look at Alzheimer's disease. What is it? What causes it? And can we treat it?
The Naked Scientist comes to you from Cambridge University, and it's supported by the EPSRC and Rolls-Royce. I'm Katie Haylor, and thank you for listening. Until next time, goodbye.